Thanks for the opportunity to be in this seminar or webinar rather. And I am just going to sort of share our experience in Singapore. I'm calling this the PECS journey from field environmental chamber studies to field studies. So let me just get started. On this slide, you kind of see uh, the work that we've been involved in and doing for the last 2 decades or so. Um, Back in the early 2000s, we were involved in what we call the thermal indoor air quality chamber studies. Even though we call this a chamber, it's like a room within a room, and it's still like a normal office room where you would have workstations and people could go and experience and be exposed to the conditions there. So that was a setup where we had a dedicated air handling unit serving separately for the personalized ventilation devices, air terminal devices, and then a separate background system. Then moving on into the 2007, 2010 kind of time frame, we had by that time developed our own field environmental chamber setup. This is converting two of our existing rooms in our department and making them kind of a dedicated research facility, but it's still like a real life building and normal office workspaces, and subjects could go and occupy the space there, and then they can experience the conditions. That also had dedicated AHU to serve separately the personalized ventilation devices, and then another air handling unit that takes care of the background system. So you will see from the way I'm describing, it was both background systems and personalized ventilation that we were constantly studying in our suite of studies. We had the opportunity then in 2009, 2015 timeframe to actually install personalized ventilation in a building outside. This was our retrofitted zero energy building of our Building and Construction Authority Academy building. And it was a room, it was a space that had, I believe, about 12 occupants who could occupy that. And I will talk a little bit more about those details in a bit. And that was a place where we had personalized ventilation integrated with an underflow air distribution system. Then we moved on further in 2011, 2015 timeframe to now look at another interesting aspect of this personalized environmental control system framework, where we said if we could have a local extraction, what we call a personalized exhaust, how would that help? And this was done in a simulated healthcare setting in the same thermal IQ chamber that I mentioned as our starting point. And we continued our studies until 2018-19 timeframe with a little bit more simulation-based focus. And I will also talk a little bit about that and then present to you where we are moving forward. So one of the very first studies we did was a desk-mounted personalized ventilation integrated with ceiling supply systems. This is our very first setup some 23 years ago in the thermal IAQ chamber. As you can see here, these are the different workstations where people could go and experience themselves, expose themselves. We had a PV-ATD and then a background system that could be either mixing ventilation through ceiling supply diffusers or through a displacement ventilation diffuser. So again, personalized ventilation combined with a background system. That was the study. So these are the protocols. I'm not going to say exactly what we did, but it was a comprehensive protocol. We checked the background conditions, personalized conditions. We did thermal comfort parameters, indoor air quality parameters. We measured the ventilation effectiveness. And of course, we asked the people whether they liked it or not, the subjective response. So this is a very snapshot overview kind of a slide where when we compare with the background system only, that means 26 degrees ambient, no personalized ventilation, that's zero there. And then we have the 15 liters per second as part of the background ventilation system. If we compare that as the baseline, that's 1 as the ventilation effectiveness, all the personalized ventilation conditions were significantly higher than that, somewhere in the range between 1.4 and 1.8. Now, obviously, we will notice that if you have a background that is warm, say for instance, the first bar, background is 26 degrees, and then you have the personalized at 23 degrees, and you get kind of the highest ventilation effectiveness. That says a lot about the potential to save energy, because the warmer the background temperature in our application, which is hot and humid, the better it is from an energy point of view. And of course, the effectiveness being higher means it's going to be much more beneficial for comfort and indoor air quality considerations. And sure enough, our thermal comfort acceptability sort of a slide, it clearly shows when you use PV, it's always been perceived to be much better. Very acceptable is on the upper part of the y-axis, and the same goes for the indoor air quality acceptability as well. The subjects whom we ask them to participate in a kind of a proper design matrix, they always found when they used the PV and when they were exposed to the PV conditions, it was much better. Now, this is something that we did back then, probably the first time and the only time we did it, where we measured the temperature of the exhaled air of a person very close to the nose, about probably I would say an inch away from the nose. And what you see here is the red line is when you don't have the PV, right? It's about 28 degrees thereabouts average over a length of time. The blue line is the background is 26 degrees in the room and the PV is 20 degrees, cooler PV condition. You notice that the blue line is about 2 degrees lower at all times. Now that's critical from a perceived air quality perspective. The personalized ventilation strategy provides that microenvironment or breathing zone condition to be always perceived to be on the cooler side, very evident from the exhale air temperature measured here, and that goes a long way to show why the occupants also feel that the air they are inhaling is cooler, and that makes them feel better. This is also in line with some of the other studies that we have seen in the literature, and we also probably heard from the previous speaker. So I spoke about the potential to save energy if the background is warmer. We did this at 26 degrees. It can be even higher. I will talk a little bit about the higher temperatures as we move on in the presentation here. Then the next one that we did here, again, during that kind of time frame, we are talking about ceiling mounted PV. That means the PV devices are located up on the ceiling combined with the mixing ventilation. And what this showed, this is a setup in our new environmental chamber at the time. This is still 20 years old now. So we had these devices that could come from the top, or we also had the desk mounted. So there are two different types of experiments that we were doing here. This particular one on this slide is the ceiling devices combined with the normal background mixing ventilation. And clearly, as the PV airflow rate increases, you find the perceived air quality also increases. Very clear evidence to show that the PV ATD was working well. Now, of course, because the PV device is a little bit higher in terms of the location relative to the microenvironment breathing zone, it is not probably in the same league as something very close to the person. So to that extent, there was a little bit of slightly reduced performance for the ceiling supply or ceiling located or ceiling mounted PV devices. Okay, let me go to the next one. This is the desk mounted PV system. Now we're looking at the PV devices located at the desk, but integrated with an underflow air distribution system. The same field environmental chamber, and you can see some of the tests in progress then. We also had a mannequin deployed to use that as a part of our comparative analysis. And these devices, primitive as it may look here, they just had simple degrees of freedom of up and down or to the side. So the person also had the opportunity to adjust it whichever way they want to within a given degree of freedom. So this slide tells us a little bit about the advantages of what the PV was doing in the context of underflow air distribution integration. On the left-hand side of the y-axis, we have the perceived inhale air freshness. So low on this, 0 or 10 means poor freshness, 100 means very fresh. And likewise, the perceived inhale air temperature on the right-hand side y-axis, low means it's cooler, higher number means it's warmer. These are not absolute degrees Celsius. They just mean higher number means warmer, lower means cooler. Now, the acceptability of perceived air quality. If you follow the inhale air temperature, the cooler the PV temperature is, the better it was. More people found it, more acceptable. The trend line going down this way. Cooler means more acceptable. And when it comes to the freshness, Higher the freshness means more acceptable. Again, these might sound very intuitive and logical, but we were able to establish through our studies at the time. I now fast forward a little bit and get us to the stage where we had the opportunity of installing these devices in an actual building outside. This is not in our own department building. It's in the retrofitted building of the BCA Academy. It was the zero energy building, sort of a demonstration that we were on about with a much wider team. So what you're seeing here is this space where you see the green line. These are the desktop PV air terminal devices. They are very similar to what we saw in the previous presentation by Maria, something that is kept on the desk, but it is not, it's not fixed. One can move it around on the desk. And then we had the underflow air distribution as the background system to the space. Now, to the left of this figure on this side, we also were studying together in this particular study, just the displacement ventilation air terminal devices. The space on the right-hand side, which is the conventional sealing supply, mixing ventilation supply air diffusers. Now we were trying to measure the air exchange effectiveness or the ventilation effectiveness characteristic. So you notice here that the green shaded region, these are the AEE values when personalized ventilation with underflow air distribution was used, or for that matter, the DV alone was used, and they were significantly higher. And that's something we would expect. They would have a higher AEE value, which goes to show the benefits of such systems. And compared to, on the right-hand side, the red shaded zone, it shows the conventional AE values that you would expect. So relative to the mixing ventilation, which is typically around 1.1 at best, we see 1.6, 1.7, that sort of air exchange effectiveness with the personalized ventilation integration. Now, as I said, 2011 onwards, we were trying to look at the advantages of a personalized exhaust system combined with a personalized ventilation. And this was part of a study that we were aiming to look at in a healthcare setting where you have a consultation room, where you have a doctor, like this is the doctor here, and then on the left-hand side, the breathing thermal mannequin was our infected person patient. So what happens to the movement of infectious aerosols as the sick person entering the doctor's room is going to be exposing the other person. So we said if we had a chair that is integrated with an exhaust device, like you can see here, a top personalized exhaust or a shoulder exhaust, and if that chair and the person is moving together, there is an element of local control. And how does that combine with a doctor in this case on the left-hand side, the healthy person, and if that person is always going to get the personalized ventilation. So this was a case of studying different scenarios, only PV or only personalized exhaust, or the two working in tandem together. The main objective is to protect the doctor from any infectious aerosols coming from the sick person or infected person. So I'll just go very quickly through the performance indicators that we got here. Personalized exposure effectiveness, it rises with PV airflow. And you can see here both with the 5 liters per second and 10 liters per second. We tried both mixing ventilation and displacement ventilation as a background system. So obviously they were showing to be much better, the improvement with the PV. This slide is the busy slide. All you need to note is the height of the bar, the first bar in each of these plots, that is with no personalized ventilation or no personalized exhaust. And you notice that the intake fraction, the amount of infectious aerosols inhaled by the healthy person across the distance, was always significantly higher. All the other bars that are reduced, like T10, S10, what it means is when you use a personalized exhaust device, it significantly cut down the intake fraction. So the personalized exhaust with the patient or with the infected person that is in the chair was able to reduce how much aerosols gets transferred to the healthy person or the doctor across. Very clear evidence that we notice over here. Exposure reduction, another performance indicator. So if you have a sick person across a table where you had a chair with the personalized exhaust helping to do a local extraction, and then the doctor on the other side has personalized ventilation, or you could just use only the personalized exhaust for the patient, the exposure reduction, how much exposure reduction you get for the doctor. The higher this indicator, the better it is. You notice that when there's only personalized ventilation for the doctor, it is beneficial up to about 50%, ranging from 30 to 50%. But when you bring in the personalized exhaust for the patient, it goes up to in the order of 70% to almost 90%, whether it is with mixing ventilation, top exhaust device use, or the shoulder exhaust device. Again, just to illustrate how it was beneficial, and this particular subject became very interested to a lot of, I suppose, people all around the world, and during the COVID time, that is, and it was seen, as mentioned earlier too, personalized ventilation, if we can combine that with a local exhaust as well, will help us in a long way to design systems to mitigate the transfer of infectious aerosols in any space. So just to show these indicators how they went, all indicators as intuitively expected, we were able to document through those studies. I now move on to towards my last couple of slides, last couple of strategies that we were exploring. This is the one PV system with chill beams. So we were looking at this strategy here where we said the chill beam needs an induction principle at the chill beam, which is typically the outside air, used to induce the room air. We said, let's not do that. Let's take the outdoor air and supply as personalized ventilation in the workstation. However, the chill beam will still be driven by a local fan to provide that background, cooling effect done purely as an active chill beam. So that was the concept. We studied this through energy simulation. And here you notice here, compared with the conventional variable air volume system, single airflow distribution system, when you have a personalized ventilation at the desk and a local activated chill beam or active chill beam, the energy savings was quite significant, as you can see from this slide. We also did a CFD simulation study to show how the microenvironmental air distribution moved around. This is the kind of modular concept we were studying, the CFD. The top slide is VAV. All the temperature everywhere in the room is about the same, 24 degrees. Whereas with the PV active chill beam, we let that thermal stratification occur. By that, even the contaminant stratification would take place. And we noticed that we were able to see benefits, 100% load, 75% load, as the load reduces, which means when you don't have people, you can literally, turn it off completely, but we don't want to do that. But certainly we can reduce it significantly. However, where there is a person seated, you have the localized, personalized ventilation really working well in the microenvironment of that zone. So now let me summarize my presentation today, this afternoon. This is what I started off with. We did very early studies at the start of the millennium, thermal indoor air quality chamber. Then we went on to build our own field environmental chamber, again, mimicking a real building outside. It is, again, part of our facilities that we use for teaching purpose. That's what we had converted. Then we had the opportunity around 2009-10 to install in a totally different building, nothing to do with our educational buildings on campus. And there we were able to demonstrate the PV integrated with underflow air distribution. And then we went on to look at exhaust, local exhaust, and some simulation studies. So where does the future hold for us? What are we doing now? So we need to look at more applications. There's interest here in Singapore, but we don't have too many field applications. There's one that is interesting, and we'll probably hear more about this in the near future. This is the one with the living lab for the mixed mode ventilation in the tropics. My colleague, Dr. Adrian Chong, is in charge of that. And you would notice what you see here is these devices here on the panel of the workstation through which one could have a local spot cooling kind of an air supply or air distribution. Again, this has just been completed last year, and we would have more information about this in due course of time. And with that, I would like to end my presentation. Thank you for your attention. I'll pass the screen back to Bjarne.